So whenever our classifier predicts yes, sometimes it's incorrect and sometimes it's correct. So that means that sometimes the patient actually doesn't have cancer, but our classifier says he does have cancer. But other times, the patient does have cancer and we do correctly predict that. So when we're measuring precision, we're measuring how many of the times that our classifier predicted a positive class is our classifier actually correct, or was a patient that had cancer. Okay, so that's precision. And I want you to maybe pause this video and spend time thinking about the difference between these two. So these two, in English, when we're just speaking English, right, and we don't know anything about machine learning, we might refer to both of these accuracy, right? So something that has a high precision, in machine learning, we might just be like, oh, it's a very accurate model. And this is also very accurate, but they have very different definitions and they measure two very important different things, right? And the same thing with recall. In the case of recall, this time it's TP over TP plus FN. So we're answering the question, how often are the positive instances classified correctly as positive? So TP plus FN, these refer to all the patients that actually do in real life, they have cancer. But some of them we might have predicted as not having cancer, even though they do have cancer. So we want to know, out of all the patients, of the 0.1% of the population that does have cancer, how many times among them have we been able to successfully predict as having cancer? So this is the important measurement for this particular problem. We want a high recall. Ideally, a recall of 1, like 100%, right? Because we don't want to ever predict that somebody that actually doesn't have cancer, right? Because then they'll just continue living their life, not knowing that they need treatment, and then they'll die, right? And so we want to prevent that. So for that particular problem, recall is important. But notice that, again, take your time to really understand, go back to the confusion matrix and really understand the difference between precision and recall, and these questions, right, that we're trying to answer with each, and understand it very well and how it corresponds to different contexts or different problems. Because in some problems, and I'm going to give you examples of this in the following slides, but some problems need a high precision as opposed to a high recall. They don't care about the recall being high. Or some, they want a high recall, like in our case. We don't care about the precision being high. We don't care about the positively predicted classes are always correctly predicted as positive, because we don't care about falsely diagnosing somebody who doesn't have cancer with cancer, but we do care about falsely diagnosing somebody who doesn't have cancer as not having cancer. Okay, so I'm not sure if I said that correctly, so I'm going to repeat myself. We don't care about falsely diagnosing somebody who doesn't have cancer with cancer, right? Because that's relatively harmless. But we do care about diagnosing somebody who does have cancer as not having cancer, because that could potentially be fatal. So that's the importance between precision and recall, and there is a trade-off between them. So as recall increases, precision does decrease, and as precision increases, recall does decrease. So that's why it's very important for you to know, based on your problem, for you to understand and realize which of these metrics you're trying to maximize. Now, there's a very useful metric called the F1 score that combines precision and recall into a single metric, and this is the formula for it. So essentially, it's 1 over precision plus 1 over recall, or in other words, 2 times precision times recall over precision plus recall. So this aims to combine both of them into a single number, into a single metric, so you don't have to calculate both precision and recall, or you don't have to think about both of them. In a majority of the problems where it's not really critical, like the cancer problem, where you have a very high value for one or the other. So generally, you want to have a high value for both, right? A model that has a high precision and high recall is generally better. Aside from those edge cases, like the cancer problem, that's generally what you want to aim for. So it's essentially a weighted average of precision and recall, and it gives you a value between 0 and 1. So 0 would be a terrible value for the metric, so a terrible model, and 1 would ideally be the best model based on this metric, the F1 score. So it'll only be high if both recall and precision are high, and it favors classifiers that have similar precision and recall. So that's why it's particularly useful, again, in those problems where it's not really that important for you to maximize one of them. And the F1 score favors classifiers that have similar precision and recall, but this is not always what you want, okay? Again, it's very important to understand your problem. Sometimes precision is more important, sometimes recall is more important. And here's a very quick example of how the F1 score prefers models that have similar precision and recall scores as opposed to having a wide difference between them. So for example, this model has a precision of 0.5, which is not bad, but it's not particularly good. It's just in the middle, and it has also a recall of 0.5. But since they're both similar, right, they're both the same at the same level, the F1 score is 0.5, whereas a model might have very high precision, which is very good for, if that's what you're looking for, but it might have very low recall, then the F1 score also amounts to being 0.5. So, even though this has a very high precision rate or measurement, it has the same score as the one here. So it's important for you to understand this so that you know when you need F1, when you need the F1 score, right? If you just care about overall even balanced model, with a similar precision and recall, which are both relatively good, and then, F1 is what you're going for. Otherwise, you might just have to focus on looking at precision specifically or recall. So an example of when to prefer precision over recall or recall over precision is when you build a classifier that detects videos that are safe for kids. So this is essentially the inverse of the cancer problem. Remember, in the cancer problem, we said that we want a high recall. We want to always predict correctly the cases or the patients that do actually have cancer. And we don't care about the precision being so high. So this is the opposite or the inverse to when you want to detect videos that are safe for kids, right? Because now you need a classifier that may reject good videos, which would correspond to a low recall, but keeps only safe ones, high precision. So remember, in the cancer problem, we were okay with predicting non-cancer patients as having cancer. That was relatively safe for us. That mistake, that error is relatively safe for us. In this case, that would correspond to having classified some bad videos as good, so the kids would be exposed to bad videos, and so that's not what we want. In this case, we want the other side to be stronger, which is we're okay with the classifier incorrectly classifying good videos as bad because it's not, it's harmless for a kid to miss viewing a particular video that might be good because it was classified as falsely, as opposed to him viewing a bad video on accident because it was falsely classified as a good video. Okay, so this is very hard to grasp. I completely understand, and it took me a while to grasp this as well when I first learned this. So please take your time, pause the video, think about this, think about the difference between this classifier or this problem with the videos and the cancer problem, and how they're exact opposites or inverses of one another, and how so in this case, precision is more important. You want a high precision and a low recall, or a low recall is okay. And in the cancer problem, you want a high recall and a low precision is okay. So take your time to really understand these two problems. And again, this is the cancer problem. So a classifier that identifies the patients with a rare cancer at an initial screening stage. We need a classifier that detects all patients with this rare cancer. So we want a high recall, basically a 1. And then a higher precision is a bonus, because that will reduce the number of follow-up tests, but it's not harmful. It's not going to harm anybody. It's not fatal, right? So these two examples are very important for you to understand, and really understanding them will really give you an edge and a very solid base for solving classification problems. So there is a precision recall trade-off, as I mentioned. So it's ideal to have both precision and recall to be high, but this is often not possible. So increasing precision reduces recall and vice versa. So this is something to keep in mind. Classification models compute a score or probability for each class. And when the score or probability is greater than a certain threshold, the instance is assigned to the positive case, and otherwise it's assigned to the negative case. So by changing this threshold, which is a hyperparameter, remember we talked about hyperparameters, and so this is a hyperparameter which basically defines the way the model would be set up. So by changing this threshold, or by changing how sensitive the model is to assigning an instance to a positive class versus a negative class, we can change the trade-off, or we can change the precision and recall score. So we can play with the trade-off between precision and recall. If the threshold is raised, right, it becomes more difficult for an instance to be classified as positive. And so this increases the precision, but the recall decreases, okay? And again, don't hesitate to go back and refer to the confusion matrix to make sense of what I'm saying here. Now, if the threshold is lower, it becomes easier for an instance to be classified as a positive class. So it becomes easier for the classifier to make the mistake of falsely classifying negative cases as positive. And so the precision decreases and the recall increases. So this trade-off, again, goes hand in hand with these two examples that I gave for you to understand the importance of what's going on here, so you can really understand the difference between the different classification problems and know how to approach solving them. So to find the best, you can plot the precision versus the recall for various thresholds. So you can run the model, you can fit the model using various thresholds and plot the precision and recall, and then you can select the threshold that gives the best precision recall trade-off for your classification task. Or you can plot precision versus recall for various thresholds and select the best precision recall trade-off for a task. The closer the precision recall curve to the top right corner, the better the classification model, because that would mean, we're going to see in the following examples, but that would correspond to the highest precision and the highest recall value. So now, instead of doing all of that, we can use what's called an ROC curve, which basically does that, but it summarizes it in this curve, right? It's called a, nobody really knows this, but it's called the receiver operating characteristic curve. Nobody refers to it as that, right? We always call it ROC curve. I actually had to look that up while making these slides, but it's another common tool used with binary classifiers, and it's similar to the precision versus recall curve. So it's essentially giving you the same data, but allowing you to view it in a different way. And it plots the TPR, or the true positive rate, against the false positive rate for various thresholds. So remember, the true positive rate is TP over TP plus Fn. Okay, so it's another name for recall or sensitivity, and it measures the rate of positive instances correctly classified as positive. And then the FPR rate, or the false positive rate, is FP over FP plus Tn, and it's the rate of negative instances incorrectly classified as positive. Again, go back and refer to the confusion matrix to make sense of this. Now, when we plot these, we get a curve like this, and this essentially gives you the trade-off. Have the higher TPR or recall, the more positive, the more false positives you would naturally have. Okay, there's no way around this. There is this relationship where as the true positive rate increases, the false positive rate will also increase. So you essentially want to select the best TPR, FPR trade-off for your classification task, right? You can't select a model that has a 100% true positive rate, because then it would also have a very high, almost 100% false positive rate, which you don't want. You want the model that has the highest possible true positive rate while keeping the false positive rate as low as possible. So ideally, the false positive rate would have to be 0, but then you'd have a very low true positive rate as well. So you have to find the balance, you have to find the trade-off, and a very good way to do this is by plotting this and picking the top, furthest top left corner possible, because that is the ideal point here, where your true positive rate is as maximized as possible while keeping the false positive rate at a relatively low value. So this is also important for you to understand this trade-off. So take your time, right? Pause the video and take your time to understand this relationship. Now, the dotted line corresponds to our classifier that randomly guesses. So if you just have a classifier that randomly guesses, just flips a coin and predicts if it's false or positive, this would be the ROC curve of such a classifier. And so the better the classifier, the further up into the left corner this elbow goes into. So you can have a classifier that's less good, right? And it would maybe have a curve like this. So, you want it to be above this line, because otherwise your model is no better than flipping a coin. But the more pronounced this elbow is, or this corner is, the better your model, because the higher the true positive rate you can achieve with a lower false positive rate. Now, this is a good way to show what I was trying to explain. So this is the random classifier here. And ideally, right, you want a model with a 0 false positive rate and a 100% true positive rate. And that would correspond to this point here. But, right, in practice, that's impossible. So you can try and get as close as possible to that corner, but there's always going to be a curve here. So you pick the point that's closest to it. And then, you might have different models that are worse, right? They get further and further away from this perfect classifier here. And a good way to instead of having to always plot this and find the spot and then find the corresponding value and then get the threshold for it, etc., we can use a metric called the AUC, or the area under the curve. And so ideally speaking, if you know how to measure the area of a triangle, you would know that this triangle, assuming that the curve goes straight down from here and straight over here, the area under it would be 1. So that would mean that the perfect classifier would have an area under its curve corresponding to 1. Now the random classifier has a 0 area. It's just a line. There's no triangle, right? Now, as the model gets better, the area under its curve increases. So the perfect classifier would be 1, and the random classifier would be 0.5. Okay? So the worst model you can ever have, that's even worse than a random classifier, would be 0. So you want to have a model that has an AUC that's higher than 0.5, right? Because the closer it is to 0.5, the more similar it is to just a random classifier. And ideally you want it to be 1. So anything between, so generally we say that 0.7 is good, 0.8 is really good. You don't want to be close to 0.5. You don't want, 0.6 is not really that good, but it's still better than a random classifier. So the higher the AUC, the better your classifier is. Now, multi-class classification can distinguish between more than 2 classes, as we said, as opposed to binary classification, which distinguishes between 2 classes. And some algorithms, such as random forest classifiers, which we will learn about in this course, are capable of handling multiple classes directly. So random forests are really amazing. You can do regression with them, you can do classification with them, you can do multi-classification with them. So we're definitely going to be learning about them, and they're very useful and almost any type of problem you might encounter. Other algorithms, such as support vector machine classifiers, which we will also learn about in this course, or linear classifiers, are strictly binary classifiers. Okay. Now, various strategies exist to perform multi-class classifications, and I mentioned this briefly in the beginning of this video. And they use multiple binary classifiers. So there are 2 ways to do this. I'm sure there are others as well, but these are the 2 main ones. One versus all, abbreviated as OVA, and we also have 1 versus 1, or OVO. So I'm not going to be going into those, but know that they exist. And if you are interested, you can go and learn about them as well. And these are my references for preparing this slide or this presentation, if you want to check them out. And these are actually the slides that I used in college for my course that I was talking about, right? And yeah, I'll see you in the next video. Bye-bye.